we're now going to hand over to Cadence. Deepak Pant, I think he's come over from India.
Yep.
Thank you.
Yeah, so good afternoon. I'm Deepak Pant. I'm the R&D lead for IFE, and I have come from India to attend this conference. So, when my boss said you should go, I thought it was too long a trip, right, just to attend a conference. But now that I'm here, I'm really happy I came. I've not seen so many formal users in a room, excited to do formal debating and discussing. So for an R&D guy, it's very satisfying to see this, the tools getting used. Whether it's Cadence tools or other tools from a technology point of view, I've spent years in formal, and it's good to see this community. With that, I'll start. So the focus of my presentation here is how formal can play in overall verification management and planning cycle, how formal can, formal results, you can take formal contribution in your overall metric-driven flow. So I heard a number of you here, I've heard this before from other customers, we spend time and effort doing formal, and most of the time, when we go back, our managers asked, or whoever is managing the project, they want to know what have you done, and they want to see metrics that quantify the effort and results that formal has given, right? And it's always been a challenge. So with that context, I'd like to just talk about what Incisive does and how we handle this. So this is the typical verification, planning, and management cycle. Oops, what happened? Yeah. So you have the planning part where in terms of Cadence tools, you use we have something called ePlanner, where you can document your verification plan. You can tie your verification goals to specific goals in the verification plan, and then you move on to developing your test benches in the simulation world, and sort of linking back the tests to individual goals there. And in Incisive, what you can actually do is do similar things with your assertions, right? So you develop your assertions, or you use pre-packaged assertion-based VIPs, or other VCOMs that you either have or you've got from somewhere, and you can actually type them back to your the verification plan that you've developed there, similar to what you would have done with tests in case of simulation, right? And the interesting part is that once you've developed these, and then all the three engines, the Incisive engines that actually support assertion-based validation. We have IEV and IFV that do formal. We have IES, which is the simulator, and then there's a box, right, Palladium. So assertions can also be synthesized in a box, and all three of them actually support the same database, coverage database. So the coverage information from the assertions and SVA, PSL covers that are developed there. All the coverage and status information can actually be dumped in the same format and in the same database by any of the verification engines that can support assertions. And then using the same analysis tool, which is vManager or Enterprise Manager, you can actually pull up all this data together, and data from all the three technologies can be actually seen next to each other, right? And it can be merged. So multiple formal runs can be merged, multiple simulation runs can be merged. You can actually see the data together, and you can analyze it together. You can merge the data across hierarchies and take it to the top level. So various, if you are in different stages of your verification cycle, you can actually the data can be rolled up. So with this, you can actually have formal contributing to the overall verification, planning, and management cycle. So I'll talk about this in a bit detail later on in my presentation. So for metric-driven environment, verification environment, there are two main components of that. One is the code coverage component, and then you have the functional coverage that you want to track, right? And so for code coverage, we have what is the coverage unreachability app. This is similar to what Mark and other people talked about today, and so this is how Formal can help in achieving code coverage closure in the verification cycle. So this is I'll go over this in detail, but before I dive there, just a few minutes on verification apps. Other vendors also have a similar concept, and so just a small list of apps that we have. There are more, but not captured here. So being an R&D guy, a formal R&D guy, nothing would please me more than actually working on new and more advanced solvers, right? Working on algorithms and solvers. But our field guys keep telling me basically they keep echoing what Chris said today in the morning, right? There's a big hurdle in adoption of Formal. Some of it is real and some of it is perceived, right? And so it's important for tool vendors to actually recognize that and refocus the Formal efforts to actually come up with pre-packaged solutions that help them achieve their overall verification goals, and not just focus on complete verification of IP blocks, but actually see how they can complement simulation-based environments and actually target specific problems. And I'm glad to see that almost all the vendors here are actually moving along that direction, right? So hopefully that will address some of the concerns and actually bring down the resistance to Formal adoption. So this slide shows 5 apps that we have. We have superlinting, which is relevant more to designers early on in the cycle. We can do a lot of structural checks. Along with that, we can also do, by structurally analyzing the design, we can actually automatically extract a lot of checks, a lot of covers, so dead code, FSM, X checks, X propagation checks are coming in the next release. We have the toggle checks, so all sorts of checks can be extracted automatically and run. It's all a push button solution, very little effort. So for a designer, very quick feedback when they are actually developing the design. Protocol compliance. This is if you're doing protocol verification, interface verification. So we have a bunch of ABVIPs for common protocols. They are actually optimized for Formal to run better in Formal. They're also supported in simulation and Palladium, but they're primarily optimized in Formal, not just for performance, but also we have some built-in debug capabilities, since there are ABVIPs, and our tool knows, as it can actually do a better job of debugging them. So that's the protocol compliance app. It's various from a project lifecycle point of view across multiple phases. It can be used. Then coverage unreachability, I'm going to talk in a bit detail about that. Register map validation, a pre-packaged solution where based on an IP exact specification of a register map, we actually generate all sorts of checks to do reset value checks, to do access policy checks. So that's all the checks are generated automatically, and you can be done in AFI and COT. Again, a lot of debug capabilities are built in the app. This came out, first release came out about 6 months back. So more stuff coming in later on this year in this space. So again, this is an area where we found Formal to be quite helpful for those of you who've run into problems like register map validation problems that fell through simulation, especially if you have register aliasing and stuff. Those are things that Formal can actually handle very easily. Yeah. SOC connectivity, one of the oldest apps that we have, and as we've seen in earlier presentations today, very simple to use, a high-value app, very simple to use. Okay. So apart from these 5, there are other applications. There's low power. There's a low power application that's coming out. Then we have solutions that are, these are solutions that are mainly tailored to mainstream verification engineers, complementing simulation, very push button, completely packaged, so that you don't really need to know formal technologies, the experts in formal, or know the tool lot. Then there are other such applications which are more targeted towards formal users. We have data path verification, checks, scoreboarding. So there are a bunch of applications that we have apart from that. Right. So there's just a digression from what the main topic of my presentation was today. So now moving on to coverage and reachability. I'm just building this thing. So you run your simulations. You've generated your coverage numbers. You're towards the end of your verification cycle, and then you have the last set of uncovered elements there. So, and now what you need to do is actually try and cover it. A lot of this is manual effort, very time consuming, not very easy to do. So the big question is whether it is reachable or unreachable, whether you are actually putting in all the effort that you are putting in trying to reach this particular, these 2 lines that are uncovered, is it actually useful, or it's just going down the drain. So this is, right. So if it is reachable, if it's actually reachable, that means the test suite is incomplete and you actually need to put in this effort and write more tests. On the other hand, if it is unreachable, it could be there could be 2 possibilities. Your design was in the configuration that you were using for your DUT was actually, it was okay that this is unreachable. It's expected. Or there's a design bug which causes this unreachability, and then you go and fix it. So how do you get this information? You run your simulations, you dump coverage in the coverage database, and this is your normal coverage simulation flow. You look at the coverage in your coverage. Okay, so this information is available and you can eyeball it, you can look at the waveforms, and this can be helpful for you, but this is not not sacrosanct, the reachable this thing. It's just based on what your environment is where you're running this. Yeah.
Can I supply top level constraints to it?
Yeah, you can. You can. So you can. It's the value that you'll get both in terms of the unreachables you'll detect, and the quality of the the traces that you'll see depends on how much investment you put in. Right? So the easiest one is just put it in the regression. It's uninitialized, but you'll still get some unreachables. You put initialization sequences, they'll increase. If you put more constraints, valid constraints, the unreachable information, number of unreachables will also increase. Right. So this I already mentioned. Yeah, so this is how it comes up. You pull up the database in IMC, and there is a new mark there on the side which says it's a UNR, and user can actually go there and kind of exclude them, and the tool will actually based on whether it's expected or not, and the tool will automatically adjust your coverage numbers and bring that down, right? Since we released it, it's been quite successful. A lot of our customers are using it. Saves a lot of review cycles for whole analysis. This was actually much better than we had expected, but seems this is a big pain, and people did like it. So number of papers on this already. This is one from one of our customers. There was an EE Times articles from Fujitsu. Some codes there. So we have a number of customer success stories on this flow, well adopted. I think one of the bigger reasons of the success is also how easy it is to use and plug in. So people try it and without any effort and actually see some success quickly. So this was one aspect of metric formal helping out with MDV and helping you reach coverage goals. The another aspect is what we call enriched metrics, which is basically formal. This was code coverage, and this is more what we'll talk about is more about functional coverage and how seeing formal results, pure formal results alongside simulation results. So how can this help? How can rolling up formal results along with your simulation results, functional results, how can that help? You can actually highlight functional unreachability. So if you have a methodology where you are you're writing SVA covers or PSL covers and also doing simulation, right? In that case, you can do unreachability, a similar unreachability analysis for SVA and PSL covers using vManager. Okay, so this is available, and you can take credit for formal work, which is basically whatever work that you've done. If it's a part of your proper verification planning process, it becomes a part of your project management goals, and it gets tracked, and it's given the same importance as you see for simulation. Okay. What this can also help you is if you've used when you're doing block level formal verification, and if you've used written constraints and assumptions there to as a part of your formal environment, when you take that block up and actually run simulations, what you would like to do is verify those assumptions. So you can add those assumptions as actually assertions and run it in your simulation runs, and you can see this information side by side, whether things that were assumptions here have passed in the simulation runs. It's a good way to correlate. Okay. Yeah, this slide shows how you can actually see unreachables. So simulation, you ran your simulations, and the first one here is the data here is actually it shows the simulation data, and one of the blocks here is coverage, and the other one is status. Right, the percentage one shows coverage, and the other is status for the simulation. And so there's a simulation hole there that's 0%. You see 0% there, right? But can it be reached? You run formal on it, and this shows formal thing, and formal shows 0%, and there's a marker there which basically says that this is unreachable. So this is a status that that simulation can never show, right? Unreachable for a SV or PSL cover is not something that you can ever get in simulation, and you can see it side by side, and you can say, okay, so this was a hole, and this is unreachable, and I should forget about it, right? So this is basically a way of achieving the same coverage unreachability flow, but for functional covers. Okay, another interesting capability we have in IEV, Incisive Enterprise Verifier, is that when you use formal to hit a cover, or when you use formal to prove an assertion, what we can actually do is generate a trace, which is the waveform that you see, right? So we can actually generate a trace and then replay it in simulation, right? So these traces are small, and they deal with only the cone of influence inputs that are in the cone of influence. But if you have a good constrained environment, we can actually solve the complete set of inputs and actually generate a good test vector for you, right? And when you replay that, if you have your test ready, or test bench environment ready, right, that also gets executed. So this is another way of getting contribution from formal, of generating coverage data from formal, which is actually exactly like what you get from simulation. And this is something that you can also roll up in your planning process. So this slide actually shows how what you can do with UVM. So if you have a UVM test bench and you have your formal environment ready, you can actually configure the UVM test bench as a passive test, which basically means you turn off your sequencers, so there are no drivers coming from the test, right? What actually happens is, if you write good functional covers and SVA or PS, using SVA or PSL, and then you run formal, the tool will actually generate traces for that, and those act like the drivers. So you don't really need the drivers from the test bench here. And when we replay it, so the tool internally transparent to the user actually runs a simulation run, and using this trace, and during the course of that simulation run, the UVM test bench will also get exercised, and we will harvest coverage information from. So you can have your scoreboards, all your monitors, checks, everything on, and these will get exercised and get dumped into the coverage database the same way that you would have in a simulation run. So this is another way of mapping formal results to coverage results in a form that is done for simulation and is understood by project managers, and is understood, can be rolled up along with your simulation metrics. And you can use vManagers to actually see all these results. So this brings me to the end of my presentation. Formal, can help in coverage closure. It can actually add a lot of value. We've seen that with the coverage unreachability app. You as a formal users, you already understand, a lot of you already understand the value that it brings in, and we see that you're struggling convincing your management or getting contribution of whatever efforts that are put in formal. So if you find a corner case bug, that's value, visible value. But beyond that, it's a struggle, and this is something that can help you with that. Yeah.
Okay.
Questions?
Thank you very much. Any questions?
Yeah.
Alex?
Yeah, so my question is about figuring out why things are unreachable. So do you have a methodology for that?
So we have a methodology, but it's mostly around identity. It's very manual. It's not tool based. So you basically write more covers and try to find that. You can use triggers. Yeah, that it's manual, not automated right now. This is one thing that we are focusing on. We are getting a lot of requests from customers, and more so with the unreachability flow out there. The next step, people are asking, why is this unreachable, right? So that's up.
Any more questions? Yep. Tim?
So related really. So once you've done this analysis on your unreachables, and then, which is great, so then you say, okay, this should be unreachable, so you mark it as okay, but then your code changes. Is there any way of mapping the things you've already analyzed onto your new code?
So if the code changes, then you can't really map directly, right?
Well, it might be that you identify your...
So there are, to some extent we do. So this the tool that is there, IMC, it actually, you can dump out the file, and they have a checksum based mechanism of figuring out. But if there's a direct change in the area of where it is unreachable, then you cannot.
Yeah, but if it's not in the area, it's unreachable.
Then yeah. So it's yeah. Okay. You can do it. So they use checksums and all to see whether the code is where the code has changed and things. Yeah. What happened?
to follow up on,
okay. Yeah,
so just
sorry.
follow up on the gentleman's question over there. Could you not, and just to explain why something is not covered, and it's not automated, but with that, can you not, you generate cover assertions to check if indeed something is unreachable. You can negate that, and then the counterexample would be an indication of why something is not
do that yourself,
unreachable.
Right? You can kind of do that process yourself as well.
Yeah, that's right. Yeah, I understand. So there are automating that.
Yeah, so there are actually multiple things you can do. You can look at the expressions and create terms, and then see what are unreachables and when. So this is not automated right now. That's what I'm saying, and we are exploring ideas like this and see what we can actually automate and make simpler for people.
So I have a question on the UVM environment. So it seemed that you were generating transactions which you could then replay through your passive test bench to generate
what you can
coverage.
So what even if you forget UVM stuff, any formal tool, when you run when you have targets that you hit coverage targets, if you write SVA covers or whatever, right? Or if you have assertions, then we can generate traces for them, right? Witnesses for how they would for them. So these are basically a set of values that you can give to an input and to all your inputs, and then they are guaranteed to take the design to that particular state, right? So what we do is take these traces, extend them using, by solving the constraints that you specified, and then internally replay them on the simulator, right? And then the simulator is actually, so UVM test bench is not something that a formal tool will understand. It's unsynthesizable, right? So, but the simulator that's running inside that, it can handle it. So, you run it and it gets executed, and you get all the information that you would have got, you would have gotten in a simulation.
Okay. Okay. Any more questions before? Yeah. More questions.
Actually, I'm interested in knowing about the merging of results from the formal database to informal runs and the simulation-based runs. You showed that you can bring up results from the formal and simulation side by side.
Yeah.
So, those will be, those will be separate. How we can know that we have tested this in informal and this in simulation-based environment? Can we kind of create a...
So formal and simulation results are semantically different, right? A formal pass is a very, very strong pass compared to a simulation pass, right? And so you can't really directly merge both of them. So similarly, for a cover, a formal fail is a very strong result compared to this thing. In fact, in formal, if we have bounded passes, that itself is a very strong result compared to a simulation pass, because you've actually, to a certain depth, you've actually explored the complete state space, which a simulation run can never do, right? So you can't really merge them together. You can actually, only thing you can do is you can see side by side the same target, the results you see side by side. You can merge, you can roll up the hierarchy. If you are, from a block level you are going to a cluster level or a chip level, then the same way, the way you roll up the simulation results, you can also roll up the formal results. One way, if you do the the UVM thing that I showed, right? If you go the replay path, then the data that you get dumped, that gets dumped, is actually exactly like simulation, right? But that's again a linear data, it's right. So we are taking one trace and replaying it. So it's like one simulation run. That can be merged as a
infinite state space.
Yeah.
So this replay feature could only be used for specific cases. You can't run that all of the stuff in formal. Then there is no use of. Then you have to go back to simulation. If you want to play back all of those traces into your formal, right?
I didn't get you. So you're saying the formal explored, infinite traces, but actually gave you only one. That's what you're saying?
No, actually with formal, what you are doing is you are kind of exploring the infinite state space, right?
Yeah.
Now, when you are using the replay feature, you can't use that to replay all of those infinite spaces. You can only do some specific cases with that replay feature. Because if you are doing that, then you are going back to simulation again. So there is no use of that.
That's true.
So that's what I was interested in, to know that how you can place this formal with simulation-based verification methodologies, so that you can make, you can do those in parallel, knowing that we have an extra level of verification layer or whatever. But merging those, if you are not able to merge those together, then
but you cannot. You
are putting extra effort on you.
Formal results are different, right? Semantically, that's where you can't really say that it's merging a formal pass with a simulation pass will devalue the formal pass. Right? You seeing it together, and if you see it's passing in formal, it's a different thing.
Okay. Thanks, Steve. And one question online, which is a question. Can you briefly explain a bit about your UPF solution?
So our UPF solution. Okay. So I'll just. It's still, it's not out there yet. It's in beta, so I don't know whether I'll talk about this. But it's mostly we support UPF, and we all functional verification, all the apps that I talked about in context of power aware designs, right? So they can be used in with UPF in place, right? And then there are certain other apart from functional verification, all sorts of functional verification with UPF in place. Apart from that, there are certain other add-on information that we generate, which I don't think I'll do it yet.
Okay, maybe you can ask people individually. Okay, thank you very much. Thank you.